Okay, we're going to finish up Chapter 6, Part 5, and we're going to start with inelastic collisions. So at the end of Part 4, we talked about elastic collisions. Well, in an inelastic collision, your two objects are going to approach one another, they're going to collide, they're going to stick together, and they're going to move off together with a common speed. So let's do a problem. So in this problem, we have two 10,000 kilogram railroad cars. So we have mass of 10,000 kilograms, and we have it moving at a speed of 24 meters per second. So that's our mass 1, and that's our speed 1. It strikes an identical car at rest. So identical car, the mass is going to also be 10,000 kilograms. And that car's at rest, so it's 0. The cars are locking together as a result of the collision. What is their common speed? So we typically refer to the common speed as v prime, and that is what we're looking for, that common speed. So we know that our initial momentum is going to be the mass of 1 times the velocity of 1 plus the mass of 2 times the velocity of 2. So therefore we have 10,000 kilograms times 24 meters per second plus 10,000 kilograms times 0. So our initial momentum is going to be 2.4 times 10 to the 5th kilograms meters per second. Now we know it's an inelastic collision, so they lock together. We're asked to find the common speed afterwards. So we know momentum, that initial has to equal final. So my initial momentum is 2.4 times 10 to the 5th kilograms, meters per second, and that equals our final, which the cars still have a mass 1 plus a mass 2, but now they're moving with a common speed that we're calling v prime. And v prime is what we're going to solve for. So we're going to divide both sides by m1 plus m2, this by m1 plus m2. Those go away, and that's going to give us v prime. So v prime is going to equal 2.4 times 10 to the 5th kilograms meters per second divided by 10,000 kilograms plus 10,000 kilograms. So v prime is going to be 12 meters per second. Okay, let's try another one. So here we have a 8-gram bullet is fired horizontally into a 9-kilogram block of wood, and it sticks in it. The block, which is free to move, has a velocity of 40 centimeters per second after impact. What is the initial velocity of the bullet? Okay, so we're given the mass of the bullet to be 8 grams, so we know we got to change that to kilograms, so that's going to be 0.008 kilograms. We're given the mass of the block to be 9 kilograms. We're given the velocity of the block to be 40 centimeters per second. So we know that has to go to meters. So in 1 meter, we have 100 centimeters, which is going to be 0.4 meters per second. Now we know initial has to equal final, and we are looking for the initial velocity of the bullet. Okay, so we're looking for VI of the bullet. So our initial, when we start off, we just have the mass of our bullet times the initial velocity of our bullet. But now finally, because the bullet sticks into the block of wood, we have the mass of the bullet plus the mass of the block of wood times the velocity of that block of wood. Okay, so the mass of the bullet is 0.008 kilograms. We don't know the initial velocity of the bullet. That equals the mass of the bullet, which is 0.008 kilograms, plus the mass of the block is 9 kilograms, and that's multiplied by the velocity of the block, which is 0.4 meters per second. Okay, so all we need to do is rearrange and solve for initial velocity of the bullet, and when we do that, we get the initial velocity of the bullet to be equal to 450 meters per second. Okay, and then the last thing in your chapter we want to talk about is having to do with airplanes, balloons, and rockets. Conservation of momentum also applies when you're in flight. If you were to just look at the airplane, then momentum's not going to be conserved. It has a zero momentum before its takeoff, and it might change during the flight. But if we consider the system of the airplane plus the atmosphere, the momentum is going to be conserved. If you look at the propeller-driven airplane, you have an interaction when your propeller is pushing against the surrounding air molecules, and that's going to increase their momentum in the backward direction. Okay, that's going to be accompanied by an equal change in the airplane's momentum in the forward direction. Why doesn't the airplane continually gain momentum? So as it's going through the air, it's actually hitting the air molecules, and it's going to give those air molecules impulses in the forward direction. That's going to produce impulses on the airplane in the backwards direction. So if I'm doing a straight level flight at a constant velocity, the two effects are going to cancel each other out. Now, we can also have this holding true for rockets, and that explains why they're used in space flight. A rocket is going to have that change of momentum in the forward direction by expelling the gases at very high velocities in the backward direction. If I choose the direction that the gases get expelled, then the momentum changes, and that can be used to change the direction of the rocket. So a jet airplane is somewhere in between the propeller-driven airplanes and the rockets. What a jet engine does is it's going to actually take in your air from the atmosphere, and it heats it to a high temperature, and then it's going to expel that at that high speed back out of the engine. Okay, so even though the gases do not push on the atmosphere, the jet engine requires the atmosphere as a source of oxygen for combustion. Okay, this ends chapter 6.